In this video, we're going to focus on logistic equations and how to derive the general solution. But first, let's talk about the difference between exponential growth and logistic growth. What do you think the difference between the two is? So on the left side, this is going to be an exponential curve. And on the right side, we're going to have a logistic curve. An exponential curve increases at an increasing rate. It's unlimited. It grows forever. There's no limit to its growth. A logistic curve, initially it increases exponentially, but then it begins to increase at a decreasing rate. And eventually the graph is horizontal and no longer increases. It reaches its maximum. This maximum is known as, let me choose a different color. It's called L, which is the upper limit, also known as the carrying capacity. A logistic curve is very suitable to describe population growth. For example, let's say if you put 100 cats on an island, and that island has a lot of food. Those cats are going to eat up the food and multiply. And as they multiply, you're going to have more cats eating up more food. However, the resources of that island is limited. There's only so much food that the island can produce. So eventually, the population will grow into a point where it can't grow no more. There's a certain limit in which the land can sustain its population, and that is the carrying capacity. So the number of cats in an island won't grow to infinity. It's not possible. Eventually they're going to run out of food and they won't be able to multiply. So in a logistic growth, you have limited growth. That really describes the population of a group of species on the island. So make sure you understand the difference. Exponential growth is unlimited, logistic growth is limited. Now, what is the differential equation for exponential growth? And what is it for logistic growth? For exponential growth, the differential equation is dy over dt is equal to ky. T is the variable on the x-axis, and y is on the y-axis. Now for logistic growth, dy dt is equal to ky times 1 minus y over L. Right now, I'm going to just give you the equations, and then later we can talk about what they mean. Actually, it might be wise to go over it now. If we look at the equation on the left, as y increases, dy dt increases. So what does that mean? Well, as the population increases, the rate at which the population increases will increase as well. For example, let's say if you have 1,000 rabbits on the island, and at that level, let's say the rabbit population increases by 100 every year. Well, if it increases by 100 per year when the population is 1,000, how much do you think is going to increase when the population is 2,000? It's going to go up by 200 per year. So as you can see, the population growth rate is basically proportional to the population level. So dy dt is proportional to y. The more rabbits you have, the more you're going to get over time. Like the rate of rabbit growth is going to be higher if there's more rabbits on the island, if that makes sense. Now, what about a logistic curve? As y increases, dy dt increases as well. In the first part of the graph, you can see that it looks like an exponential curve. Now, notice what happens if we take the limit as y approaches 0. So when y is very small, what's going to happen to the expression y over L? As y approaches 0, y over L will approximately be equal to 0. So therefore, it's going to be ky times 1 minus 0. 1 minus 0 is 1. So you're going to have ky times 1, which is just ky. So dy dt is equal to ky when y is small, which is basically the same equation as what we have here. So when y is small, the logistic curve behaves as an exponential curve. It increases exponentially. When there's not many rabbits on the island, and if there's a lot of food on the island, the rabbits, they're going to multiply fast. They're going to eat up the food, have babies, and the population is just going to explode. Now, what about if y approaches a large number? It can't approach infinity because the population has a limit, which is L, the carrying capacity. So if that's the maximum y value, what happens when y approaches L? As y approaches L, y over L is basically approximately equal to 1. If you replace y with L, you can have L over L, which is 1. So thus you'll have ky times 1 minus y over L is 1, so 1 minus 1 is 0. And ky times 0 is going to be about 0. So dy dt is 0. dy dt is basically the first derivative of y with respect to time. And the derivative is basically the slope at any point on a curve. So the slope is 0, which is what we can see here. The slope of a horizontal line is equal to 0. So as y approaches L, the population doesn't increase, it basically levels off. The rate of change becomes 0. As y approaches 0, the logistic curve behaves exponentially. So those are a few things just to keep in mind. Now the next thing you need to know is the general equations for these two types of graphs. Now, for the exponential curve, y is equal to c e raised to the kt. This is the general solution. In terms of population, you can write it this way. P of t is equal to p initial e kt, where p initial is basically the constant c. Now, for logistic curve, it looks like this. Y is equal to L divided by 1 plus b times e raised to the negative kt, where L is the carrying capacity, k is the relative growth rate, it's a constant, and b is another constant that you have to deal with. So this is the general solution for a logistic curve. And if you want to, you can replace y with p of t. Now, starting with the differential equation, dy dt is equal to ky times 1 minus y over L. From this equation, how can we derive the general equation for logistic curve? How can we get this equation? Y is equal to L over 1 plus b times e raised to the negative kt. What can we do? Well, the first thing we need to do is multiply both sides by dt. That's the first step. So dy is equal to ky times 1 minus y over L times dt. Now the next thing we need to do is we need to divide both sides by y and 1 minus y over L. So these will cancel. And so on the left side, we have 1 over y times 1 minus y over L dy. And on the right side, we have k dt. So now we need to find the antiderivative of both sides. Let's focus on the left side first, because that's going to take some work. We'll get back to the right side. Now the first thing we need to do is we need to modify this equation. We need to use partial fractions to put it in a form that we can integrate it in. But first, let's multiply the top and the bottom of the fraction by L. So on top, this is going to be L. Now we're going to distribute L to the two things inside the parentheses. L times 1 is simply L. So this is going to be y times L. And then we're going to have minus L times y over L. The L's will cancel. And so you're just going to get y. So this is what we now have. Now you can't multiply this L by y because that y is already multiplied to what's inside. If you do, you'll be multiplying those terms 2 times. So just be careful with that. So this is what we now have. Now let's use partial fraction decomposition. So L over y times L minus y, we're going to set it equal to some constant a divided by the first part of the denominator, which is y, plus some constant b divided by the second part of the denominator, which is L minus y. Our goal is to find the value of a and b. To do that, let's multiply both sides by the common denominator, which is this. So we're going to multiply every fraction by y times L minus y. So if we multiply this fraction by this term, these two will cancel. And so on the left side, it's just going to be L. But I'm going to write it as 1L. Now, if we multiply y times L minus y by a over y, the y variables will cancel, leaving behind a times L minus y. Now, if we multiply this fraction by this term, L minus y will cancel, leaving by. Next, let's distribute a to L minus y. So it's going to be AL minus AY plus BY. And that's equal to 1L. And I'm going to write plus 0. 1L is the same as 0 plus 1L. Now I'm going to separate the terms that have L from the terms that don't have it. So on the right side, this is going to be A times L. And then negative AY plus BY, which is the same as BY minus AY, I'm going to take out a Y. So it's going to be plus B minus A times Y, if you factor out Y. So I'm going to rewrite this expression on a new page. So it's 0 plus 1L, which is equal to A times L plus B minus A times Y. So 0 is the same as 0y. Now here's what you want to do. Since L is equal to L, then the coefficient in front of L, which is 1, must equal to A. So therefore we could say that A is equal to 1. And that's how partial fractions work. Now the coefficient in front of y is 0, and here it's b minus a. So therefore we could say that b minus a is equal to 0. And since a is 1, then b has to be equal to positive 1. So a and b are both equal to 1. Now let's go back to the equation that we had earlier, which was L divided by y times L minus y. We said it was equal to a over y plus b over L minus y. Now since a and b are 1, this is going to be 1 over y plus 1 over L minus y. And you could test it. If you combine like terms, if you combine the two fractions, let's say if you multiply this fraction by y and this one by L minus y, you should get what's on the left side. So this is going to be L minus y over y times L minus y. And over here, this is y times the same thing on the bottom. Now, because we have the same denominator, we can add the two fractions. Negative y plus y will cancel. negative y plus y is 0, leaving behind just L. So on top we have L, and on the bottom, y times L minus y, which is this. So therefore we know this process is correct. Now going back to the formula where we had the integration of 1 over y times L minus y dy, which is equal to the antiderivative of k dt. So now we can replace this expression with 1 over y plus 1 over L minus y. So now let's go ahead and find the antiderivative. The antiderivative of 1 over y is simply equal to the natural log of y. And the antiderivative of 1 over L minus y is going to be the natural log of L minus y. But the derivative of L minus y is negative 1. So we're going to have to add a negative sign. Because if you differentiate ln L minus y, it's negative 1 over L minus y. And you got to multiply by this negative 1 to make it positive. So that's why we have to add the negative sign. The antiderivative of k dt is k times t, and then plus the constant of integration, plus c. Now we can combine these two natural logs into a single natural log. Here's a property of natural logs that you've learned in algebra. ln a minus ln b is equal to ln a divided by b. So therefore, ln y minus ln L minus y is equal to ln y divided by L minus y. And all of that is equal to kt plus c. So if ln y over L minus y is equal to kt plus c, we could say that e raised to the ln y over L minus y is equal to e raised to the kt plus c. Since this is equal to that, and since e is equal to e, then everything on the left side, e raised to the ln y over L minus y, must be equal to e raised to the kt plus c. Now e to the ln, those two functions are inverses of each other. They will cancel. And so you're going to get y divided by L minus y on the left side. Now, we need to separate kt from c. To do that, let's go back to algebra. X cubed times x to the fourth is basically x to the 3 plus 4, which is x to the 7. We need to take this form and split it into two parts. So x raised to the 3 plus 4 is equivalent to x cubed times x to the fourth. Therefore, e to the kt plus c must be equal to e raised to the kt times e to the c. Now, if we look at the formula, the general solution for logistic curves, we know it's L over 1 plus b e to the negative kt. Right now, we have e to the positive kt, and we need to introduce a negative sign. So what do you think we should do to the formula at this point? How can we introduce that negative sign? What we need to do is raise both sides to the negative 1. That's how we can add it. Whenever you raise a fraction to the negative 1 power, all you need to do is flip the fraction. So this is going to be L minus y over y. And on the right side, because these two terms are multiplied to each other, you can distribute the negative 1 exponent to both. So it's going to be e to the negative kt times e to the negative c. Now c is a constant and e is a constant. A constant raised to a constant is simply a constant. There's no variables there. So we can call this just one constant. We're going to call it b. And that's how we're going to get b times e to the negative kt. So now let's multiply both sides by y, so that this will cancel. And so what we now have is L minus y is equal to y b e to the negative kt. So now let's add y to both sides. So L is equal to y plus y times b e raised to the negative kt. On the right side, let's factor out the GCF. The greatest common factor is y. Y divided by y is equal to 1. This term divided by y, the y variables will cancel, and you're just going to get b e to the negative kt. So now the last thing that we need to do is divide both sides by that expression. And if you do that, L divided by 1 plus b e to the negative kt is now equal to y. So this is the general solution of a logistic equation. That's how you can derive it from a differential equation. Now let's work out a problem. 100 dogs were released on an island in 2005. By 2012, there were 324 dogs on the island. The island can sustain a maximum of 5,000 dogs. Assuming logistic growth, write a general equation that describes the population P of t at any time t. So we know the general equation is y is equal to L over 1 plus b times e raised to the negative kt. In this case, we're just going to replace y with P of t. And that's going to be L over 1 plus b e raised to the negative kt. Now, in 2005, t is equal to 0. That's when everything started. So we could say that P of 0 is 100. At t equals 0 in 2005, there were 100 dogs. By 2012, which is 7 years later, so t is 7, that means P of 7 is 324. Now the problem stated that the island can sustain a maximum of 5,000 dogs. So 5,000 is the carrying capacity, that's L, the upper limit. So with this information, we need to solve for two variables, b and k. Now the first point that you should plug in is the initial point. P of 0 is equal to 100, so let's start with that. So P of t, when t is 0, that's going to be 100. L is 5,000, and this is going to be 1 plus b raised to the b times e raised to the negative k times 0. K times 0 is simply 0. So what we have is 100 is equal to 5,000 over 1 plus b times e to the 0. Now e to the 0 is basically equal to 1. So what can we do at this point? How can we solve for b? Well, let's cross multiply. 1 times 5,000 is 5,000. And then we have 100 times 1 plus b. So now let's divide both sides by 100. 5,000 divided by 100, you can cancel 2 zeros, so you get 50 over 1, that's just 50. So 50 is equal to 1 plus b. Subtracting both sides by 1, b is 49. So now let's just get rid of a few things. Let's get rid of that. And this 2. So therefore, we know that b is 49. Now let's use the second point to find the value of k. So t is 7, therefore P of 7 is 324. L is still 5,000. B is 49 times e raised to the negative k, and t is 7. So what should we do in order to solve it this time? Well, let's begin by cross multiplying. So we have 5,000 is equal to 324 times everything in the bottom. always running out of space. Now, if we divide both sides by 324, 5,000 divided by 324, that's going to be 15.432. And that's equal to 1 plus, we don't need the parentheses anymore. So it's 1 plus 49 e to the negative 7k. Subtracting both sides by 1, we're going to have 14.432 is equal to 49 e to the negative 7k. And then 14.432 divided by 49, that's going to be a decimal number, that's 0.29453. And that's equal to e to the negative 7k. At this point, what you want to do is take the natural log of both sides. And the reason why you want to do that is so that you can take this constant and move it to the front, which is a property of natural logs. Also, the natural log of e is equal to 1. So negative 7k times 1 is simply negative 7k. So to find k, now we just got to divide both sides by negative 7. So ln 0.29453 divided by negative 7 will give us a k value of 0.1746. So now we can write the general equation. So P of t is equal to L, which is 5,000, divided by 1 plus B, we know B is 49, times e raised to the negative kt, or negative 0.1746 times t. So this will give us the population at any time t. Now, how many dogs will there be by 2020? So if t is equal to 0 in 2005, by 2020, t should be 15. 2020 minus 2005 is 15 years. So we need to find the population when t is 15. So all you got to do is plug in 15 into this equation. Now you can type this in all at once, but for some of you who may not have that type of calculator, I'll go ahead and do it one step at a time. So the first thing you want to do is multiply negative 0.1746 by 15. And so this is going to be negative 2.619. E to the negative 2.619 is 0.072876. E is basically the inverse of the natural log function. So that's how you could find it in your calculator. Next, let's multiply 0.072876 by 49. That's about 3.5709. And then add 1 to it, which is 4.5709. 5,000 divided by 4.5709 is about 1,094 if you round it to the nearest whole number. So that's how many dogs will be on the island by 2020. You're going to have 1,094 dogs. So now let's answer the next part of the problem. Part C. In what year will the population reach 1,000? So we know it has to be before 2020, because by 2020 it's 1,094. It could be 2019, it could be 2018, but let's figure it out. So what do we have to do to get the answer? What would you do? So we need to replace P of t with 1,000, since that represents the population. And our goal is to solve for t. The best way to do that is to cross multiply. So 1 times 5,000 is 5,000, and that's going to equal 1,000 times 1 plus 49 e to the negative 0.1746 t. Now let's divide both sides by 1,000. 5,000 divided by 1,000 is 5. So this is what we now have. Now the next thing we need to do is subtract both sides by 5. 5 minus 1 is 4. And then after that, we need to divide both sides by 49. So 4 over 49, well, let's just leave it as a fraction for now. Anytime you need to solve for a variable in the exponent position, you need to take the natural log of both sides, like we did before. So now we could take this term and move it to the front. So ln 4 over 49 is equal to negative 0.1746 t, and we know that the natural log of e is 1. So then t is equal to ln 4 over 49, which is negative 2.5055, and then take that divided by negative 0.1746. And so t is 14.35. So it's going to be about 14 years from 2005. So by 2019, the dog population will hit 1,000. It's going to be somewhere between 2019 and 2020. Now, how many dogs are born per year in 2016? How can we find the answer to that problem? What equation can we use? To answer that, we need to use the differential equation dy over dt is equal to ky times 1 minus y over L. But y represents the population p. So let's replace y with p. Therefore, dp dt is equal to k times p multiplied by 1 over p, 1 minus p over L. So what can we do at this point? How can we figure this out? P is basically the same as P of t. So what is the population in the year 2016? That's going to give us the value of P. So that's one thing we need to figure out. We know the value of K. And we know L. L is 5,000. And K is 0.1746. So we have everything we need except P. Let's calculate the population in the year 2016. 2016 minus 2005 is 11. So T is 11. So we need to calculate P of 11. This is going to be L, which is 5,000, divided by 1 plus B, which is 49, times E raised to the negative K, times T, which is 11. Negative 0.1746 times 11, that's negative 1.9206. And then E raised to that number is 0.14652 times 49 plus 1, that gives you 8.1794. And 5,000 divided by that number is 611. So that is the population in 2016. It's 611 dogs, but I'm going to use 611.3. So now let's calculate dp dt. But let's get rid of a few things. So dp dt is going to equal k, which is 0.1746, times p, which is a 611.3, and then times 1 minus p divided by L, which is 5,000. 1 minus 611.3 divided by 5,000. That's 0.87774 times the other two numbers. So if we take 0.87774 and multiply by 0.1746 times 611.3, then we're going to get 93.68. So that's going to be the PDT. So that's how many dogs are born per year in 2016. It's about, I guess you can round that to 94. So about 94 dogs are being born per year. Well, actually, technically, the population increases by 94 dogs per year. For instance, let's say if 100 dogs died in that year. That means 194 dogs were born. So the population increased by 94. So this is the net growth. It takes into account the dogs being born minus the dogs that are dying. So technically, that's just how much, that's how much the population increases by per year, rather than the number of dogs being born per year. So I just want to make that clarification. So to really figure out the number of dogs that are being born per year, you have to know how many are dying that year. So let's say if 300 dogs are born in 2016, how many dogs are dying in 2016? Now keep in mind, the population increased by 94. That means 300 minus 94 is 206. So if 300 dogs are born that year, that means 206, have died that year, which means that there's a net gain of 94 dogs in that year. Now, is there another way in which we can estimate this answer? How can we estimate the population growth per year? What other method can we use to get an answer that's close to 93.68? dPdt represents the instantaneous rate of change of the population with respect to time. Now we can approximate the instantaneous rate of change by using the average rate of change formula. So let me show you. Now let's make a table. In the year 2012, the population was 324. And in the year 2020, the population was 1,094. Now 2016 is right in the middle between 2012 and 2020. So the average rate of change between the years 2012 and 2020 can give us a good approximation of the instantaneous rate of change at 2016, because 2016 is the midpoint of 2012 and 2020. So to find the average rate of change, it's basically f of b minus f of a over b minus a. In this case, it's the population in the year 2020 minus the population in the year 2012 divided by the difference of these 2 years. So let's go ahead and get the answer. In 2020, the population is 1094. In 2012, is 324. 2020 minus 2012 is 8. 1,094 minus 324, that's 770. Divided by 8, this will give you an average rate of change of 96.25, which is very close to 93.68. It's a little bit off, but it's not too far away. So how can we get a better approximation of this answer? What can we do to get an answer that's closer to 93.68? What you want to do is you want to approximate the instantaneous rate of change at 2016 by choosing 2 years that are very close to it. The best 2 years that we can use are 2015 and 2017. Now we need to calculate the population at those times. By the way, in 2016, I believe it was 611.3. Now if you plug in 2015 or t equals 10 for 2015 into the population equation that we got earlier, you're going to get 523.6. And if you plug in t equals 12 for the year 2017, you're going to get 711.3. So now if we calculate the average rate of change between these 2 points, it's going to be 711.3 minus 523.6 divided by 2017 minus 2015. 711.3 minus 523.6, that's 187.7 divided by 2. That will give you an average rate of change of 93.85, which is very close to 93.68. And so that's how you can approximate the rate of change of the population with respect to time. Between 2015 and 2016, going from 523.6 to 611.3, if you subtract those two numbers, in that year, the population increased by, I need to make space to write this, so hold on one second. Let's get rid of that. So the population increased by 87.7. Now, between 2016 and 2017, you could see that it increased by 100. If you average these two, you'll see how much the population increased by. 100 plus 87.7 divided by 2 will also give you 93.85, which is the average growth rate in the year 2016. So as you can see, there's different ways in which you can calculate this answer. But that's it for this video. That's all I got. Thanks for watching.